In this session, we would understand Kirchoff law with respect to radiation, and we would understand the numericals based on Kirchoff law. To begin with, what is Kirchoff law? Kirchoff law simply says that when there is a thermal equilibrium, what would happen? The coefficient of emissivity would be equal to coefficient of absorptivity, and we can prove it theoretically as well as experimentally. So in this section we would first understand the theoretical proof for it, followed by an experimental proof, and then we'll work on some of the numericals based on Kirchoff law. To begin with, I take a very simple example to understand the concept of Kirchoff law theoretically. So this is a box. Now this is a constant temperature enclosure. Now since this is a constant temperature enclosure, within this I am hanging two balls. One ball is the ball A, which is a normal ball. The other is the ball B, which is a black body. Now, what would happen? Since it is a constant temperature enclosure, after some time, what would happen? After some time, we would see that both ball A as well as ball B attain the same temperature. So, they would attain the same temperature in due course of time, and this is because the fact that they are at a constant thermal equilibrium. As we said, at a constant thermal equilibrium, what would happen? The coefficient of emissivity would be equal to coefficient of absorptivity, and to prove that we have understood this theoretical framework. Now, let me draw certain formulas based on it, so you certain equations based on it, so you would understand it better. Let's talk about the body A first. Body A is a body which is a grey body. It is a not black body. So black body is which absorbs all the incident radiation. So B is a black body. It absorbs all the incident radiations. A does not, right? So for the case of A, we would understand the emissivity power of A could be explained as the form where I say E. Let me use some terms here. E is the emissivity power of A. Okay. A is the coefficient of absorptivity, and EB is the emissivity power of B. Clear? And finally Q, which is the radiant heat, which is incident per unit time per unit area. So Q is the radiant heat. Now for body A, I would calculate the heat absorbed. So heat absorbed for the body would be what? Heat absorbed for the body would be the coefficient of absorptivity multiplied by the radiant heat. So this would be QA for the body A. Now, for the body A, the heat emitted is how much? We already know that it is equal to E. For the body B, the heat absorbed would be equal to Q because the coefficient of absorptivity would be 1, and the heat emitted would be EB, and that's for the body B. Clear? Now, what I do is 1 divided by 2. That means E by EB is equal to AQ by Q. I cancel out Q. So I can say E by EB is equal to A, which is coefficient of absorptivity. But on the other hand, I also know E by EB is what? E is the emissivity of A, body A, and EB is the emissivity of B. So E by EB I can write also as emissivity coefficient. So it is the coefficient of emissivity. Therefore, based on this, I can prove theoretically that Kirchoff law is what? The coefficient of absorptivity is equal to coefficient of emissivity. I repeat again. Now, why does I have taken this as equal? The heat absorbed is equal to heat emitted. I can take heat absorbed equal to heat emitted when it is at constant temperature. So given this is a constant temperature enclosure, I have considered heat emitted is equal to heat absorbed. And that's one of the basic things you must know before we move further. Clear? So just a quick recap, it is a constant temperature enclosure. One is black body, other is a normal body. So after some time, what would happen? Both the bodies would land up with the same temperature. To prove this, we understand the heat absorbed by the body A would be the coefficient of absorptivity multiplied by the radiant heat, and the heat emitted would be E, which is considered as the emissive power of A. For B, it would be EB and the heat absorbed would be Q. I divide 1 by 2. So it is E by EB is equal to AQ by Q. So therefore, E by EB is equal to A, which is absorptivity, and E by EB is what? It is the coefficient of emissivity. Therefore, we can say coefficient of emissivity is equal to coefficient of absorptivity. Now, this was a theoretical verification. Coming on to a practical verification, what I do is, I take a U-shaped manometer. Now, in this U-shaped manometer, I have mercury which is filled. And this is a colored liquid, okay. Now, there are two boxes which are connected to it, which is P and Q. Now, this is Q, this is P, and in between there is a valve, and here you have R, and this R is where hot water influx takes place, and this is R. Now, understand this carefully. One side of each of this is black body. So if I am keeping it like this side, the shaded side that I have drawn here is a black body, and the other side is a polished side. Now understand this diagram. What I am trying to do is, this is a manometer. So the pressure exerted by the air in P and Q on the liquid would be the same. Now, R is in between, with one side is black body, the other side is polished body. Initially, all three are arranged in such a fashion that each of them have the same side as polished, the other side as black body. But this R with hot water is rotating. Now when it is rotating, what would happen? At some point, this black body would come close to this black body, and at other point this polished side would come close to this polished side, but this R is rotating. Now this R, since it is rotating, the heat incident per unit time on the polished surface would be what? It would be KAEB, and that is the heat incident on the polished surface. Okay, and what would be the heat absorbed per unit time? So the heat absorbed would be AKAEB, which is the coefficient of absorptivity along with it. Now the heat radiated here would be what? In this case would be AE, and the heat radiated in this case would be KAE. So I can say the E by EB would again be equal to A, which is the coefficient of absorptivity here, and this E by EB is again equal to the coefficient of emissivity. So therefore, I can say on the incident side or the polished side, it would be equal to the absorptivity into K into A into EB, while on the other side, which is the black body, it would be KAEB, and therefore this would be equal to, the ratio would be equal to the coefficient of absorptivity. So the simple idea is with a simple experiment that we have done. Now let's move on to some of the numericals for the same. So here what we know is, we know the area, we know the value of Q, and we know the time. Now what we have to find out is the emissive power of the surface at a given temperature. What is emissive power? Emissive power is equal to QA into T. So Q here is how much? 1260 divided by 15 into 10 raised to power minus 3 into 40 Solve this and you would have the emissivity power or the emissive power of the surface at a given temperature. So this is the formula that you use here. Simply solve the value. I am not solving it here. The idea is to help you understand the basic formula. The next is 512 joules of radiant heat are incident on a body which absorbs 224 joules. What is the coefficient of emissivity? Coefficient of emissivity is equal to coefficient of absorption. Now here we are talking about absorption, right? So based on the Kirchoff law, we have already proved it. Now this coefficient of absorption would be QA by Q. So QA, which is Q, the heat absorbed divided by the heat incident. So how much it is? 224 by 512. So somewhere close to 0.5 would be your answer, less than 0.5, okay, would be your answer, because this gives me 256. So this is less than 256. That means it is less than, somewhat less than 0.5. So this is how we calculate the coefficient of emission or coefficient of emissivity. Another question similar to it. The emissive power of a sphere of an area this much has an energy this much. So we know this is what? This is Q, this is A, and this is T. Again, what we need to find out is the amount of heat. So, the emissive power is given. So this is not Q, this is E, which is the emissive power, right? We know E is equal to Q by AT, and what we have to find is amount of heat. That means Q. Right, so Q is equal to EAT. So E here is 2100 multiplied by 0.02 multiplied by 20 second. That gives me the answer. Since it is joules per meter square second multiplied by meter square multiplied by second. So all of these would cancel out, because this is joules per meter square per second, and this is meter square and this is second. So meter square and second would cancel out, and I would have the final answer in joules, right? So this would give me the amount of heat, the value in joules. So the total energy that would be there would be given in joules. I simply solve this question. Now note, in this question emissive power is given. Okay, so the language of the question is important. In the previous question, it was clearly mentioned that the body emits this many joules. So this is Q, which is given. The heat emitted is given. So the Q value is given. Now the next question, the energy is again given. So the Q is given. Radiated in 5 minutes. So the T is given. The surface area, which is A, is given. Now the emissive power. So again, E is equal to Q by AT. Q is equal to 6000 divided by 5 into 60. I would convert it into minutes into second, multiplied by 100 centimeter square. I need to convert it into meter square. That's the standard unit we use. Okay, so this would be 100 into 10 raised to power minus 4 meter square, and therefore this would be my emissive power, and that's how we calculate it through this formula. So those were some of the simple questions which we have done based on Kirchoff law, a very important concept, as I mentioned, and commonly asked in your examination, highly scoring, a simple formula to apply, and all your numericals could be solved very quickly based on Kirchoff law. Now note, this Kirchoff law is different from the electromagnetic laws that you would, the electricity laws that you would understand, the current and the electricity. So note that we also have a Kirchoff law and radiation, and don't get confused. Stay tuned for many updates from our side for sciences. Have a wonderful day.